Donald Tharp is a graduate of Abilene High School. He has a BS in chemistry and an MS in organic chemistry from Abilene Christian University. He has worked as a chemistry and physics instructor at Cisco Junior College. He was a supervisor for the University of Abilene Health Department Laboratory. He has worked at the Texas Department of Health and the Texas Water Commission as a registered sanitarian, concentrating in surface water treatment and the solid waste programs. Don has worked for the TNRCC, TCEQ, and solid waste, wastewater, and public drinking water programs since 1993. Retiring in March of 2011, he is currently consulting with the TCEQ Texas Optimization Program in areas such as regulatory records review, data audits, monitoring and process control, on-site laboratory instruction, filter assessments, and assistance with plant startup. Please welcome Donald Tharp.
It's been a long time, some 46 years, that I've been traveling the state and a couple of times out of state and even a couple of times outside the U.S., working in water and trying to help people make good drinking water. What we want to talk about today is really just a tour through a surface water treatment plant. I know most of you here are probably surface water treatment plant operators, but I'd like to go at each station that we're going to stop and talk about some of the problems that you might run into at each one of these points in the treatment process. There's all kinds of issues that you can find with intakes, particularly with the older surface water treatment plants. One of the big problems that I find, aside from some of the design issues that you can find in an intake as to where they put it and how long it's been there, is the fact that quite often we forget that we've got gates and wheels and valves and things on these things that need to be exercised. As a result, your multi-level intake that's required of you quite often all of a sudden becomes an intake that only has one or two ports that are open. So you lose the ability to take that water that's most appropriate for treatment from the various levels in the lake. As a matter of fact, in the older intakes, the bottom two intakes are quite often completely silted in, particularly in the older lakes. That's one of the problems that you can have. The other is that in the surface water treatment plants, little towns that are small, and they have to depend on whatever water source they can got. Jack Schultz, and he's not in here yet, but he and I was working with a little town one time, and we went out to look at their surface water treatment plant, and actually it was one of these that was extended out into the pond. It wasn't a lake, and it was hanging off a pole, and the pump was down in the water, and the darn thing wasn't much bigger than the length of this room, and he and I were looking at this intake wondering how in the world they get water out of it. The pond, the little stock tank belonged to a rancher that allowed them to have the water out of this stock pond. And it was the only water available. And Jack and I were standing there on this thing. We looked across the lake, and about 6 or 7 cows walked in and walked out into the middle of the pond, and of course took a drink of water and did their business. Well, that's an issue. It's called watershed control. They didn't have any control over it because they didn't own the water. And they needed the water, so they weren't going to say a thing to Rancher Tom at all about that. So you have an issue sometimes with watershed control, point source discharges that come into your water source, particularly in areas around your intakes. If you do something like put an air bubbler around an intake to keep that water circulating, the fishermen love to come up and tie into your buoys, because all that oxygenated water draw the fish to you, so you've got issues with control, people getting in or around your intakes. Sometimes we do treatment at the raw water intake. Quite often it's an oxidant of some sort, a pre-treatment with chlorine dioxide sometimes something like permanganate, And you have to be really particularly careful, particularly if you're treating for manganese, and you have to raise the pH to make the chemical reaction happen. And I've seen instances where they have taken day tanks of caustic and potassium permanganate, set them side by side next to their pumps at the raw water pump station. And if the caustic gets away from you and gets tangled up with the permanganate, that reaction generates enough heat that it will start a fire. And I have seen them burn up their control panels by that very method. So you have those kind of issues that where you're at the intake that you want to kind of watch. Access to the intakes, sometimes it takes a rowboat, sometimes they're on piers. It just depends on the design of the intake. You always want to have some kind of a sample tap there because you always want a sample of the raw water that you're trying to treat. Well, what kind of problems can you run into with meters? Well, first of all, if you're doing any kind of return from your ponds, the return from those ponds they should come in ahead of the meters. If you're going to do treatment in a plant, you got to know what the total flow coming into the plant is. And if you put that discharge point from your sedimentation ponds behind or upstream or downstream from the meter, well, when you kick it on, your dosages may not be correct for the total flow that's coming into your treatment. So you always want to make sure that you've got that flow coming from your sedimentation ponds accounted for so that you can make the appropriate adjustment in your treatment process. Other issues that sometimes you get hung up on, and this is really a pet peeve of mine because regulations require you to have those meters tested once a year. And quite often, what I've found is the people that do that testing will come out and they'll slap some kind of a electronic meter on there and measure the 4 to 20 milliamp signal and call that a calibration. They'll calibrate the out point from the signal generator that goes to the SCADA system, but I don't see them slap on any kind of a calibrated meter on those lines and actually measure the flow that's going through the meter. And I think measuring the calibration of that meter means finding out exactly what the flow is, not necessarily what that 4 to 20 milliamp signal coming out of that meter is. Okay, so you have to be careful about how you get your meters calibrated. You have to be kind of careful about chemical injections in and around these meters. If you've got a real hard water like we do in West Texas, and you decide to do any kind of pH adjustment in and around some of these meters, if you get the pH too high, and we'll talk about this again in just a few minutes, you can get a little lime softening effect, and you can get some scaling happen in those meters that can affect their output quite a bit. So you have to be careful about how you inject chemicals around these meters and where you put that injection point. That's another issue that you would want to look at. Mixing is real important. You've got if you put chemicals into a line or into some kind of a vessel like a flash mix or whatever, the point is to get those chemicals completely and thoroughly mixed throughout the entire body of the water and get the concentrations of the chemicals down to a point where you get the chemical reaction that you expect. These are called inline mechanical mixers that you're looking at here. I can give you an example where the engineers and the contractors were installing these mechanical mixers to a plant that had a pretty large pipe. And the flow through that pipe was such, it was what we call laminar flow. There was no internal real mixing in the flow of that pipe. So they decided that these mechanical mixers would be the thing to do to make sure that those chemicals were completely mixed. They were trying to set up a system of injection using ammonium sulfate and chlorine to do production of monochloramine. Well, they had already done their disinfection ahead of this point of injection. This was booster chlorination, basically. And they had a mechanical mixer, real fancy, big, expensive, all that good stuff. And it had an impeller down at the bottom of this shaft, but the chemical was injected through the shaft itself. It was hollow. The chemical came out right at the base of where that impeller was. Well, this water that they were treating was pretty high in calcium carbonate. And what they were doing was putting that ammonium sulfate down right at the point of injection, right underneath that impeller. Well, it raised the pH right at that point up to about 11. Well, you get the pH up around that high in hard water, guess what happens? You clabber that up pretty quick, you know, and all of a sudden they'd run it for about a day and a half, and all of a sudden their high-dollar fancy injection point ceased to operate. And they scratched their head and worried about that and fumed and fussed and went and got another high-dollar mixer just like the one they just screwed up and stuck it back in there and did the experiment one more time. It took them a couple of times to figure out that the problem was that they were having a chemical reaction right at the injection point. Now, us poor boys that have small plants that use stingers know to put one of those expandable balloons on that injection point so that it expands and breaks loose that calcium carbonate formation, and you don't have that maintenance issue. But it took these guys a couple of times and a whole lot of money to figure out that they had made a design error in that particular situation. Next example is an example of a flash mix that sometimes don't flash so well. That's primarily because they couldn't afford to replace the motors and impellers and stuff in that flash mix to actually do any stirring. And sometimes you run into that situation at a water plant. Obviously, having a replacement spare part on the shelf was not these guys' intent at all. So occasionally you have problems that you run into that look like this. Then Noble and I were at a plant. Recognize that, Noble? This is a feeder pipe that comes from the sedimentation basins, and it's feeding a gullet that feeds 3 filters. And that pipe rises up into the bottom of that gullet, and it rises up above the floor of the gullet about, what, a foot, maybe a foot and a half above the floor. And then the water spills out of this pipe and then is distributed in that gullet over to the 3 ports going into the filters. And Noble and I were looking at this. There were a whole lot of other issues about this design that we had, but we were looking at this, and the operator was saying, you know, he said, I had to stop feeding caustic. And Noble and I looked at each other, and we looked at him, and we said, yeah? What was the issue? He said, well, you know, my pH on top of filter number 1 was yada yada, 7.5, 7.6. He said, that's what it's kind of supposed to be. He said, but the pH on filter number 2 was like 7 something. And Noble and I looked at each other and said, what? And then he said, and you know, the pH on number 3 was even lower than that. So we kind of scratched our head, and Noble, being observant as he is, said, look, Don, they're still feeding chlorine. Why don't we take our chlorine test kit and see if we can figure out what's going on? So we did that very thing. We took the test kit, and we took the chlorine residuals across top of those filters. And then we went down and took the chlorine residual on the bottom of the filters. And this is what we found. Water coming up through that plant was laminar flow. Again, no internal mixing to speak of in that pipe. And when they had installed those injection points, they just went in there, and there wasn't a stinger in there. They just bored a hole in the pipe. The opening in the pipe was just flush with it. The water coming up here, they injected the chlorine here, but there's no mixing. So that plume of chlorine was dependent on the diffusion to spread out into that pipe. But it didn't have time to completely mix before it got to the pipe. So there was a concentrated plume of chlorine going up the side of the pipe. And when it got up here, all the chlorine went this way and fed into these 2 filters. And the water coming up this way, going that way, didn't have any chlorine in it at all. It was because there was inadequate mixing in that pipe because of the laminar flow. And sure enough, when we got to the bottom of the pipe, filter 3 had a pretty good chlorine residual. I can't remember what it was, but it was satisfactory. Filter number 2 had one that was okay. It wasn't too bad. Filter 3 had no chlorine residual on the bottom at all. Well, what does that do to your CT study? It basically takes out that part of D2, whatever that zone was. They lost credit for that because of the no chlorine and no disinfection at the bottom of filter number 3. Again, it's just a point of how critical mixing is. We would recommend that you put a stinger in there so it's in the center of that flow so that you have a better chance of having the diffusion of that chemical happen as a plume. And as a matter of fact, I think I've got I don't have that next slide. We usually have a slide that shows how you can use these stingers and why that cone of diffusion is so important. When you do like ammonia and chlorine, if you get the chlorine feed too close to the ammonia feed, well, the injection point right at the tip of that stinger, quill is what the engineers called it, but we call it stingers. Chlorine residual can be what, 5,000 parts per million when you're feeding that water feed? So it's real high. Well, you inject that into an ammonia water that has parts per million. At 5,000 parts per million, what have you done with your ammonia to chlorine ratios? You've burnt all your ammonia out. And as a result, you're going to overfeed ammonia to try to get to monochloramine. Again, it's a matter of mixing. That's why we say put those injection points 5 or 6 feet apart. If you don't have any internal mixing, like an orifice plate in a joint or an inline flash mixer or something like that, to get those chemicals completely dispersed so you get the chemical reaction that you're expecting to get. So mixing is really a very critical part of this treatment process. You would think that you wouldn't run into too much problem with your backwash ponds or your sludge ponds or whatever, but you can. It's a part of the treatment process that we quite often don't think too much about. Removal of the products of the treatment process, getting rid of the sludges after we get through treating our water. And there's regulations governing how you get rid of these sludges. You don't want those sludges to set in those ponds for all too long. First of all, if they fill up, and when they fill up, they run over. And when they run over, quite frankly, you're discharging to a bar ditch somewhere, and that's an illegal discharge according to the regulations. That can get you into serious trouble in a hurry, particularly if you're on the side of a lake or a stream or something like that. Illegal discharges from the source. If they get too full, those sludges can go septic pretty quick. And when they do, you go out there and you start doing return water from those things, well, they can get into an anoxic situation, which means that if you're treating for something like manganese, iron, and that kind of thing, and it gets discharged to these ponds, it can be reduced back to the soluble state. And then you kick on your feed water from these ponds to feed it back into your plant. Well, you're sucking contaminants back into your plant that you just treated for to begin with. So you can kind of screw up the conditions of your water source by not taking care of the maintenance on these ponds. The sludges out of here you can store them on site forever and ever, amen, if you so desire. But you've got to revet them so that there's no runoff from them. You've got to maintain those sludge disposal sites. If you do decide to take it off-site, they have to be handled by permitted haulers, and they have to be manifested, and they have to go to a permitted sludge disposal site. So you have to be cautious about how you handle these sludges from your treatment process. These people were taking sludge from their sedimentation basin, and they pumped it into these tanks to hold the sludge for a while till they figured out how they were going to get rid of it. They had a little pump on this sludge, on these tanks. Now, how much sludge do you think they pumped with that size of a pump? Not much, not much. So what do you think the depth of sludge was inside those tanks? And yeah, a lotta. That's a good soil. Yeah, there's a lotta in there. Well, they were pumping it to one of these. You all recognize what that is? It's one of these geothermal bags. They were pumping that sludge, or trying to pump that sludge into this geothermal bag. And I don't know how many years they had been using this bag. But basically it holds the solids, and the liquid is allowed to leach out of there, and it either evaporates or leaches on down into the soil and is gone. When I walked up on this bag, it was puffed up like the Pillsbury Doughboy. I was afraid to get too close or step on it or whatever, because you just didn't know whether it was going to turn loose or not, you know. And old Don may have been buried in a pile of sludge. You never know. They had some real solids issues at this plant, trying to get rid of them, and they tried to do it on their own. And really the design characteristics of what they were trying to use to get rid of it just wasn't really adequate. So it's an issue that you need to address, and it's a serious issue that you need to make sure is done right at your surface water treatment plant. Back when I started in the 70s, we actually had investigators that were working for the health department. Tony will verify this. They would walk up on site, and if the clarifier was round, it was a solids contact upflow clarifier, okay? And it was a matter of training and experience and time. Not all clarifiers that are round are solids contact upflow clarifiers. Some of them may be just a center-loaded cross-flow radial clarifier, you know? That happens. Not all solids contact clarifier, upflow clarifiers are round. There are some that are square. I saw some not too long ago over in East Texas that were actually six-sided, kind of hexagonal size. And they had a skirt and a center cone, and they were solids contact units, and they were functioning just great. So the shape of the clarifier doesn't define what kind of a clarification process you have going on inside it. So you really have to pay attention. And you have to walk up on top of the clarifier and look at the darn thing before you can decide exactly what the heck is going on at this particular stage in the treatment process, okay? Jack calls them cross-flow clarifiers, rectangular cross-flow clarifiers. I've got square clarifiers. I've got solids contact clarifiers. When we talk about solids contact clarifiers, you've got internal slurry recirculation, you've got external slurry recirculation. You've got some clarifiers that are designed like wastewater plant clarifiers, where they've got sludge return actually on the outside. And they use that sludge return pump just like you'd use a RAS pump for you guys that treat sewage water, to do the same thing, basically build the solids so that they can have good sedimentation with their treatment process. It cuts down on their chemical load and gives, if they're maintained and managed right, it'll give them great water coming off the clarifier. So you kind of have to come to some training processes. We put together, the optimization team has put together a lot of training sessions that we call directed assistance modules. Jack shortens that to DAM training. And we try to put that on both for our investigators and for operators so that they actually can recognize what kind of treatment processes and how they can control them and what's going on inside the various kinds of clarifiers at this station. Sometimes you can see some very strange things. How many of you have seen that at your water treatment plant? How many of you have figured out why it happens? How many of you use sprinklers to knock it down so that it'll settle out? In West Texas, now I don't know about East Texas, I'm a West Texas water treater. My mentor, Mr. Holbert, told me that I could treat water by whipping it with a stick. And that means that my water's pretty stable. I got a lot of alkalinity in it, and I can do just about anything in the world to it and not screw it up. Now, you guys over in East Texas, you got a different story. You know, you don't have that kind of stable water, and it's a little tough to treat, so you got to stay on top of it pretty well. In West Texas, if we see that, we've got two things going on. Either one, we have a watershed that has a lot of soapweed on it, or we have a we have an algae bloom going on. And in both those conditions, what we're having is oils from that vegetation or oils from the rupture of the algae cells as they die off, Gennazi oils and what have you, that are imparted into the water. Well, you take an oil like that and you bring it into the plant and you hit it with sodium hydroxide, well, that's called sponification, which is a fancy term for soap making. Well, when you make soap bubbles and you try to flock, that flock gets attached to and now you got a DAF unit, you don't have a sedimentation rate, okay? So it all comes to the surface and you have that situation going over into your clarifiers. Well, in West Texas, what they do is take lawn sprinklers and put them on the railings, and they hit that soap film with sprinkled water. It breaks up the soap bubbles, and everything goes right to the bottom of the clarifier. It's not an issue. But it is a little discerning when you walk up there as an investigator and you see that kind of thing going on. It takes you a while to figure out exactly what's happening. So it's not a real serious problem, but it could be a problem. Solids contact upflow clarifier. If you don't have something driving that internal fan inside that solids contact upflow clarifier, it ain't clarifying. There's no recirculation inside that cone. Well, if there's no circulation, there's no flocculation. If there's no flocculation, you're getting pretty bad settled water coming off the top of that thing. I walked up on top of this clarifier and he said, oh, it's been working great. We love it. Walked up there and the motor that drives the recirculation fan underneath was gone. Gone. How long has this been gone? Oh, it burned out. We had to send it off. It's been gone about 6 months. Holy moly. 6 months with no internal slurry recirculation in a solids contact clarifier is definitely an issue. Now, a lot of times they'll tell you that internal fan, the blade in there, is a mixing fan. Well, it is to a degree, but it's really there to give you enough velocity inside that cone so that you have enough circulation velocity that gives you the flocculation, the stirring action inside that cone. Water coming into a clarifier like that may come in at 1 million gallons a day or 2 million gallons a day. The recirculation rate underneath that cone is about 8 times whatever comes into that clarifier. So that fan is designed to drive that water at about 8 million gallons a day velocity. That's what gives you the mixing energy underneath that cone to make the flocculation process take place. But it didn't bother him that whole, yeah, I see you shiver, Hector. Doesn't it just make you wonder? Yes, it does. Come on up, Andy, and I'll give you a break. Andy needs to show you some information that he's got. This is Andy Waite. He's a new member of the consulting folks for TCEQ, recently retired from EPA, recently injured by working on his Jeep. So, okay.
I'm gonna try this. See, I can stand up. If I fall down, just laugh. I'm Andy, and used to be with the EPA. Golly, you already know that. We've been taking samples yesterday and the day before at the 5 to 7. They're total coliform samples. I don't know if anybody's done that. What we were doing is we were just doing a sampling, a special study, right? So we poured the water in, being very careful and stuff like that, and then we deliberately had them stick their finger in it, right? We did that 97 times because we were trying to demonstrate that it's not really as easy to cross-contaminate your sample as you might think. And I'm not saying don't be careful. That is not at all what we're trying to deliver, right? What we're trying to deliver is that if you get a positive in your total coliform, it's in the water, it's in the pipes. It's not because, you know, he waved his hand around, he had the cap upright for a minute, something else. It is, in fact, in the water. We've done it lots of places. We've done it next to wastewater treatment plants where you turned it upside down, and just left it there for 10 minutes with the cap upside down and the bottle open. We didn't get positives, okay? I'm really, really, really emphasizing, don't spend time trying to figure out how they could have contaminated the sample. Take that time and that energy into trying to see what's going on in your distribution system that caused that issue. That's all I got. Thanks.
Andy has been doing that experiment at these conferences for a whole lot of years, back when he was with the EPA Region 6, and now with us. And I'm glad that he's here and bringing the experience that he's had in his travels. Those Region 6 guys got to see a whole lot different water systems than what we deal with just in the state of Texas, because they went all over the place. Indian reservations, Arizona, Oklahoma, Louisiana, they went everywhere. So they got to see an awful lot of good things. Let's see, I'm here at the top of this clarifier, and the superintendent of this water system is trying to explain to me how this upflow clarifier is really an upflow clarifier. He was basically running a sludge blanket unit where he was the sludge was building up high enough on the outside of that cone that he was getting some kind of flocculation and sedimentation based on that water coming through the blanket. But the clarifier wasn't designed to do that. And we had a long discussion about maintenance and why that pump ought to be back. So finally it was fixed, and he went on his way, bless his heart, and we were so glad. We're glad he's retired. This is an interesting situation. In open channel flow, and my engineer friends out here will help me like this, there's such a thing as we call dynamic head inside these channels. And what that means is that water comes down that channel, the velocity of that water going through a single opening, a port, tends to drop the pressure in front of that port such that sometimes the flow through that port into a sedimentation basin is lessened to some degree. And as it moves on down that channel into the second port, it hits the end of that channel where the pressure inside that water, that dynamic head builds up, and so more of the water is forced into that second sed basin. Well, that's the situation here. It was a poor design. These are two sed basins sitting side by side. They were fed by a single channel coming down one side of them, and there was only one single port leading into these basins. There was no baffling wall, none of that kind of thing. The ports were identically the same size, and there was no way to control the size of the port, so we could not control the flow. We couldn't shut the flow off on the second port and force more water through the first, so we just had to take whatever that dynamic head would allow going into that port. And going into a single port with no dispersion wall behind it, you can see that on the west sed basin, all the sludge was built up on this side of the clarifier. Now, to an old West Texas country boy trying to do an investigation, that kind of indicates a little bit of a short circuit inside that basin. And the sludge on the east basin was all built up on that inside wall the same way. And again, I think that basin was just a little bit short-circuited, don't you? Well, when you short-circuit a basin, what happens is that the flow of water tends to speed up on this side, or on the side that's been short-circuited. Well, you see, sedimentation in a basin depends on the surface area and the velocity that's going into that tank. And when you do something like this, where you change velocity and you've changed the obvious surface area of this sed basin, you change the settling characteristics that go into that basin. So the settling characteristics of that flock, it has to settle faster than the upflow in that sed basin. If it doesn't, the upflow in that sed basin will wash that flock particle out of your sed basin and right on top of your filters. Now, what really upset me, and trust me, you really don't want to upset an investigator that's been around a while. It's bad news. This guy had the audacity to tell me that he had cleaned these basins out just 3 weeks ago. Now, son, I've been around a while, and I really don't think that was a 3-week accumulation of sludge. I really, truly don't. This is the plant that had the tanks that they were putting their solids into. This said basin was just a scooped out hole in the ground. that they had poured a concrete wall around, and there was no sludge removal in this basin whatsoever. So what they had done is taken pumps and put them on a raft, and they run that raft up and down this basin, and it was sucking sludge up off the bottom of the basin to remove it out of the said basin. It was kind of a unique way to try to do it. They had to do something, or they'd had no room for sedimentation whatsoever. But this was what they were trying to do. You can run across all kinds of innovative things that people have done when you're looking at water treatment plants. Everything in the world was wrong with this basin. You couldn't, there's no way I know that you could have designed a basin any more wrong than this one was done. But anyway, again, you run it. That's also the one where all the flocculations were gone. There was no stirring ahead of this said basin for flocculation either. This is a solids contact up close. You see the brown stuff right in here? That's not free floating flock, that's settled flock. How often do you think that it had been since they drew sludge off this basin? And again, what kind of settling do you think they got? And what kind of quality of water do you think they have coming off of it? This is another example of a basin that they tried to help a little bit. This was a centered flow, center loaded, supposed to be a solids contact unit. The water went down and came up on the outside of this chamber and out through ports. They looked at it and saw that they were having a little problem with short circuiting, so they went in here and built a sleeve around that port to try to force the water that came through here back down so that they could get more sedimentation time inside that said basin. It was, it didn't work too well, let me put it that way, okay? Again, we had some real issues with this particular sedimentation basin. This is another issue that I find quite often with solids contact clarifiers, particularly the old ones that have been around long enough so that some kind of contractor has come in and drained them down and cleaned them and painted them for you. It is really pretty important to make sure that these gates that are on the inside of this clarifier are set at the appropriate angle. And I've seen them set everywhere to where they're wide open, just straight out, or they're angled like this and angled at different angles. But there's a particular critical angle that you put them at. The manufacturer, when they built the thing, put it in that. Do you see what I'm talking about there? This is what imparts the circular motion underneath the hood. The water, hydraulically coming out of that thing, comes out at an angle and starts that circulation underneath that hood. This is what gives it the mixing energy for your flocculation inside that upflow solids contact clarifier. And I've seen these things every which way, but they need to be set at an angle so you do get that stirring action. If you don't set it, if it's wide open, that water comes out of that channel, hits that wall, and instead of going in a circular motion, it goes straight down. And you lose that flocculation energy inside that clarifier. These are usually just chains that hold them on. Sometimes they're rusted in place and you can't move them anyway, but they do need to set at some kind of an angle. This clarifier was really functioning pretty well. Do you see the kind of cloudy marble looking effect that you have right here? In a well-maintained, well-operated sedimentation basin or a flocculation basin, there will be streaks of clarified water that will occur inside your flock blanket coming out of those basins. The old timers called those mare's tails. And it's an indication that your coagulant dosage is set right. If it's set too high, those streaks will be real wide and your flock will be real fluffy and it'll float and you'll have trouble getting it coming out of the sedimentation basin. It'll be washed out of the box and right over into your filters. So you'll get reduced filter runs and reduced filter life out of your filters. There's all kinds of issues where that's affected your filters. If it's set too low, then that will be real murky looking and there won't be any mare's tails in it. It'll be milky looking and it's an indication that you don't have your flock set right. So you don't necessarily have to run a jar test. When you've been around long enough and have a calibrated eye, you can kind of look up on where the flocculators are and look over to see what this flock looks like, and it'll give you a pretty good indication of whether or not their dosages for their coagulants are set right. Sedimentation basins. If you really want to know what kind of a sedimentation basin that you have, the best place in the world to go is the set of plans for that plant, if you can find them. You know, in the older plants, it's kind of hard to run these things down. Where you usually find them is down in the bottom of the basement in an old rusted out 4-drawer filing cabinet. So you really have to kind of hunt around to find some of these plans and the specs books and all that stuff that has to do with that plant. They're around, but you sure have to hunt for them sometimes. Oh boy, this was just recently. Do you see that sludge blanket right there? This thing going on? This is a solids contact upflow clarifier, and this is the south side of the blanket. I'll give you a little closer view of it. That's what it looked like. This clarifier was running, and it looked just like that on the south side of the thing. On the north side of the thing, it looked just like that. Well, we ran a sludge judge on that thing, and on the south side where I had all of this business going on, that sludge judge was full from the bottom to the top. You know, I didn't have no 2-foot separation or anything like that. It was completely full of sludge. On the other side, even though this doesn't look all that good, he actually had about a 2-foot blanket at the bottom of that thing. And we were trying to figure out what in the world was going on with this sludge blanket. And the best that we could figure is the side of the cone on this side, on the south side of that clarifier, had ruptured. And what we were having was a jet coming out the side of the cone. And rather than the sludge going down and underneath the cone like it's supposed to, it was actually coming out of the side of the cone and creating this disturbance. The really upsetting thing about this system is that they didn't have a B operator. So they had to hire an A operator to come in once a month to sign their paperwork and overlook the operation of the plant and help kind of supervise the guys that were there. So I had an operator that had been running and supervising and doing all signing this paperwork for nearly a year. And the person had not reported that to City Hall, so, which to me was criminal. The person wasn't getting up and actually walking through the plant and actually seeing what was going on. Now, this little old town only has one clarifier, which is another issue, another design issue for this plant. So I don't know what they're going to do to repair that thing. They've got to be able to draw that thing down, get it welded up, get it filled back up within 8 or 10 hours for their holding time for the amount of water that they've got in storage. Plus they sell to some rural communities around them. So this is going to impact a whole lot of people when they try to repair this particular clarifier. But again, you can find some very interesting things when you walk up on top of a clarifier and start looking and see what's going on. And sometimes you find things in a clarifier that you just can't explain. I know if you see what that is, it's an old wagon wheel. And the best I could figure out is they were trying to stop the bowling balls from going on top of the filters. That's about the best I can tell you. Who knows? But for some reason or other, they stuck that at the end of the collection gullet at the clarifier where the water left the clarifier and headed off down to the filters. This plant was so old that they were using a serpentine flocculator. So it had been there for a long, long time. Everybody understand what a serpentine flocculator is? I'll bet none of you in here are old enough to have ever seen one. It's just a channel that goes down and then makes a turn and comes back and then makes another turn and goes down and makes another turn and comes back. And that hydraulic mixing going up and down those channels is what provided the flocculation for them in the older designed water treatment plants. Another solids contact upflow clarifier that was full of sludge. We find that a lot. They just don't draw it down. Sometimes it's been so long that since they've drawn it down that they can't draw it down because the sludge in the bottom where the blow-off is has just congealed and is basically concrete. And what they have to do is go down there and break that all up and usually take it out with mud pumps from the oil patch in our part of the country. So sometimes the maintenance on things is just amazing. With that polyphosphate, when it hits your customer's hot water heater, at about 140 degrees, it's gone, and all of your problems with your scaling ends up inside their hot water heater, and they get to replace the cost of all of that rather than you in your distribution system. So there are some issues when you talk about mud balls. Let's see if we can find some mud balls. The filter gallery, oh boy, I have seen some filter galleries and there was something down in there going, roar, come down here, we want to eat you. And no, I was not going to go down in there. No light, straight down stairwell that was half rusted through. And they expect me to go down there and see if everything's all right. I said, no, I don't think so. I'll just bet you money to dollars to holes in donuts that you got problems down there, go fix them. But I wasn't going to go down there. Filter controls, we were working with a water plant down south of here many years ago, and when we were doing an MCPE, when we rolled up on site, their coagulant pumps were leaking, and their coagulant was running out of the door of the filter gallery down the street and into a ditch. Right away, we figured we were going to have a problem with this MCPE. So we finally got to the point where we did the filter inspection, and after you do a filter inspection, you know, they draw it down, we go down in it and clamber around, play in the sand, do our thing, come back up out of it and say, well, now we want you to do a backwash. And the two operators kind of looked at each other, and one went up on top where the controls were supposed to be. The other one grabbed about a 5-foot piece of pipe and headed down to the filter gallery. The valves in that filter gallery were so bad that that person had to use that cheater bar, about 5 foot of pipe, locked onto the handle of the valves to get them to open and close. So maintenance issues can be a real problem in those kind of situations. Sample points, monitoring at the bottom of these filters. You know, you read the manufacturer's guidelines for how you're supposed to put the sample points for your turbine on your CFE and your IFE. The whole point is to tap the pipes from the side, not from the bottom, because sedimentation happens in these pipes and it'll affect your turbidity readings. Not from the top, because you'll get air in the lines and you'll have problems with your turbidity, but from the side. And it says in there, keep the run of the sample line as short as possible. Well, all operators want to run the sample lines about 20 foot down the wall of the filter gallery to a single control board where all 4 or 5 of their turbinimeters are set. They don't want to walk up and down the filter gallery making readings. They want to go to one place and look at all their readings and do all their maintenance and all that. Well, those long runs, first of all, you're not getting an instantaneous sample from that filter. So you got a filter that's you got water that's 15 or 20 minutes older than what's actually coming out of the filters. So you got a little delay there. And invariably, the lines have sags and dips and stuff in them. And anytime you have a line that has a little sag in it, well, you're going to get sedimentation in there, okay? It's just a fact. So they don't install these lines like they're supposed to, and that's another issue that you can find in a filter gallery. Testing, well, there's always an issue with maintaining the turbinimeters. When you put a turbinimeter in there, you got to take the water out of it and put it somewhere. It's got to go to waste. Well, these folks had tied that waste line straight into a sewer line, which is not right. There should have been an air brake in it anyway. But they went down to do maintenance on their turbinimeter was giving them crazy readings, jumping up and down and this, that, and the other, and then it'll settle down and read right for a while, and then it'd start jumping up and down again, and they couldn't figure out what in the world. So they went down there, they figured it was dirty. They need to go clean it, do the maintenance on it. So off down in here they go, and they take the cap off of that turbinimeter, and there was a little water snake in there going around and around and around inside that turbidimeter, giving them their erratic readings. And apparently he had come up out of that sewer line, went up the drain line, and got trapped over inside that turbidimeter. After they went home and changed their clothes, they came back and took care of the snake and the turbidimeter. So there's problems with testing sometimes. And I'm sorry to say this, but sometimes, you know, you can limit the output. You can cap the reading on these turbidimeters. And we sometimes find that. The turbidimeter will record the data as it is in the turbidimeter head. But that's not necessarily the signal that goes to the SCADA system. And where do the operators usually pick up their information for the SWMOR? Off the SCADA system. Well, we've had real smart operators that will go down and you can set the maximum reading that will leave that turbidimeter and be sent onto the SCADA system by some adjustments inside the controller for the turbidimeter. So they'll set it so that the max reading that comes out of that turbidimeter will be 4 or 5 rather than what it actually is. And so we call it capping the reading. So they never are out of compliance because the only reading that the SCADA system sees is that capped reading. But we can come in with our equipment and actually take the actual readings off the turbidimeter and compare what's actually been done against what's going to the SCADA system. And I'm sorry to say that quite often we find falsification of records because of that, you see. So there's various problems with testing when you're dealing with filters. This is an example of what the pipe gallery should look like. If you've got surface wash, you should always have some kind of a vacuum breaker or some kind of cross-connection control on those lines that go to the surface wash. Sometimes we find them, and most generally, they're in pretty good shape, but sometimes they're not operational, and that can give you a direct cross-connection between filtered water or water going to the distribution system and water coming on top of the filters, settled water. So sometimes that's an issue. The ones on the bottom are one of those readers is a loss of head reader. But there are some other control mechanisms on the bottom of the filters that you need to make sure are functioning properly. This was a filter that we were working with, again, doing an MCPE. And when you look at the top of the filter, it doesn't all look all that bad. And when we do an MCPE, we go and we put a tap on the bottom of the filter, and we put our own turbidimeter on it so that we can compare the readings from our turbidimeter with the readings that you're getting for that particular filter. And when we were down there installing our turbidimeter, the first thing we noticed was that he had an inline filter on the line, the sample line going from the filter over to his turbidimeter. And that was kind of strange. And we said, why you got that there? He says, well, I have to have that there to keep the anthracite from getting into my turbidimeter. Right away, we figured we had an issue, okay? That was our first clue. Well, we asked him to draw the filter down, and so we could look at it and get down in it. And as it draws down, the more it drew down, the worse it began to look. And when he finally got it down to where we could get down in it, that's what we found. Oh, probably the worst condition filter I've ever seen in my life. And yes, those are holes in the filter, and that's crusted stuff on top of the filter. Noble got down in there and could hardly drive a stake through that stuff that's on the top of that filter. And this hole right here went from this side of the filter all the way over to the other side. It was what, Noble, 4.5 foot across? It was huge. When we did get to where we could dig down in it, we found things like that down in the gravel. I don't know whether he could if he backwashed, the backwash water was just coming up through the holes. It wasn't lifting anything out of that filter at all. I don't think he had really had much training on what it should look like. He was just doing it the way that Billy Bob did it before he was on site. So all he had training was from another operator that didn't know much about what was going on to begin with. And that had just been perpetuated. But that was the kind of a thing that we found in that particular situation. Another place where we stop and want to make sure we don't have problems is in storage, where, the regulations call for these storage tanks to be appropriately marked. They call for storage tanks not to be inside the same container walls if the chemicals aren't compatible. So you've got to make sure they're separated. If you have day tanks, they need to have some kind of catchment underneath them, so if they do leak, that you don't get chemical over everywhere in every place. And, I told you the story about storing sodium hydroxide and permanganate together. Those two get together, you're going to have an issue. It's going to start a fire somewhere. There's enough heat there between that reaction to really give you some issues. Chemical feed rooms. The chemical feed rooms should be well marked, clean. Your chemical pumps shouldn't leak. And I haven't yet seen a chemical pump that's pumping caustic that doesn't leak. Maybe a brand new installation with a peristaltic pump, maybe. But they generally, it's pretty hard to keep caustic inside a delivery line. And when you walk up to a chemical feed situation, you sure don't want to see that. How would you like to be an operator and try to wade off into that and try to do a drawdown? I'd be afraid to step off in there, much less kneel down and try to do some work on that. That was an ungodly mess. But we finally got them to straighten it up. So chemical feed issues can be a real problem. Drawdown tubes. You've got to have drawdown tubes on your chemical feed pumps. There's a couple of reasons for that. First of all, you really do need to check your dosage rates, and you do that by doing drawdown on what the chemical feed pumps are doing. That's the real thing that tells you exactly how much chemical you're putting into the treatment process. It's not what's on the SCADA system, because there may be a mess up on the 4 to 20 milliamp signal. It may not be adjusted correctly. There can be all kinds of problems there that would give you an erroneous reading about how much chemical you're actually putting into the treatment process. Drawdown tubes are the way to do it. The other thing that a drawdown tube can do for you is that I always encourage my operators to do them on a routine basis and to do what we call pump curves. A pump curve is where you go in and you take that drawdown tube and you set your pump. If you're doing stroke and speed, maybe you want to set it on a particular stroke and change the speed 10%. And do a drawdown and find out what the 10% reading gives you. And then you record that. Then you go to the 20%, and then the 30%, and then the 40%. And you find out what each percentage of feed will give you an actual drawdown. Well, in a real crunch, if you have to make an emergency adjustment to a treatment process, using that pump curve, let's say your turbidity jumps from 30, which is pretty normal in our part of the country, not normal for East Texas, but normal for us. Maybe it goes to 150 because you had a rain event or something. Well, 150 you might look at your historical records and find the last time you did that, I set this thing on 60%. So rather than running a jar test and worrying about where you should set your feedings, you just go crank it to 50% to take care of your increased turbidity, and then go run your jar test to see where you're at. And you have an instantaneous response to that emergency condition. That's the first thing that those drawdown curves can do for you. The second thing is, if you hold them and compare them over a period of time, if your pump wears, then that pump curve is going to change. And it will give you an indication of what the condition of your chemical feed pump is, and it'll tell you, well, I need to maintain it or I need to replace it. And you can keep on top of your chemical feed rates that way. So that drawdown tube is really a very important piece of equipment to have down next to your feed pumps. I had a plant one time that, to do a drawdown, you've got to have a stopwatch with you, right? Or some kind of a watch. This plant operator took one of these electric clocks and hung it about 2 foot above the floor right behind his drawdown tube. He didn't have to take a stopwatch with him. He had that clock right there. So when he did his drawdowns, all he had to do was fill up his drawdown tube, start it, and watch what the timer was on that clock that was right behind his drawdown tube. So, you know, there's all kinds of innovative ways to do that. The next thing that we usually have a problem with, damage to our storage tanks. These things are supposed to be leak-proof and designed in such a way that rainwater won't collect and run off down inside your tank, you see. When that happens, you're putting contaminated water over into your treated water, and you're running a risk of having an issue with your treated water going to town. Obviously, there's a problem with the vents on this tank. Every tank that you pump water out of, and my engineer friends will tell me this, that tank has to breathe. If you pump water out of it and there can't be air exchanged into that tank while you're drawing water out of it, you're going to collapse the tank. And that's what's happened in this case. The vent was messed up in some way or another, and they were still pumping out of it, and the air pressure on the outside crushed the side of that tank. I was at Wichita Falls one time, and they had just built a brand new, I don't know, it must have been a several million gallon ground storage tank, concrete. Brand new, they had just filled it up. And I was there during the day, and they were so proud of showing me this thing. And I came back the next day, and the operator was just shaking his head. I said, what happened? And he said, well, I don't know. He says, I was on duty last night, and I heard this horrendous noise, and I took my flashlight and walked around. He said, I couldn't find a thing in the world that was wrong. He said, so I just went on back to the control room, didn't think more about it. He said, the next morning we got up and went back and looked at that new tank, and the entire top of that concrete tank had turned loose and went completely to the bottom of that brand new tank. So we had a construction issue on that concrete tank. Sometimes you can have issues that are just beyond your control. Sometimes when we go up, and they don't allow us the inspectors, I'm not an inspector anymore. They don't allow them to go up on top anymore. They can't climb ladders and can't walk around on top of the tanks. They can't go up on elevated tanks for sure. But if you did, sometimes you find situations like that. Now that's the inlet to the tank, but the top of the tank around that inlet has collapsed. And you can see water, well, maybe you can't see it too well, but it's actually bubbling up around the point where that pipe enters the top of the tank. So there's a problem with contamination at that point to the ground storage tank. And I can't tell you how many times I've gone up. You know, you're supposed to keep the hatches locked on these tanks and all of that. And I'll go up on top of the tank, and sure enough, the hatch would be closed and locked. And I'd ask them, well, I need to look inside the tank, open it up. And it's kind of deer in the headlights look. They'll unlock it and flip that hatch back, and half that hatch is rusted. Now, how do you rust half a hatch on the top of a ground storage tank? Anybody want to take a guess? How long that ground storage tank has been open and it's rained in it, and it's been there long enough that only half of the hatch actually rusted and the other half didn't? And they tell me that it's all been locked and secure and no contamination. And you know, that just makes me want to look deeper and harder if I was going to be an investigator. Sometimes there's just issues, that's all there is. Then we get into the monitoring business, and it's the where, what, how, why are we monitoring, and the places that we want to try to monitor. It is a situation where you need to monitor, and sometimes it's regulatory and sometimes it's not. But there always has to be points of monitoring, not regulatory points, but points where you monitor just to control the treatment process. You have to be able to do that, and you have to be able to run tests to control any treatment process that you are doing in a treatment plant. That's part of the regulatory requirement for you. Controlling the concentration of the ammonia that you inject before you inject chlorine to make monochloramine. If you don't know what the chlorine demand is for your chlorine injection point, how do you know how much ammonia to feed to keep your dosage rate such that you're on the front point of the breakpoint curve? You've got to monitor those things as part of the process control. If you're purchasing water from somebody and you're trying to booster chlorinate, how can you figure out how much LAS to put in if you don't know what the concentration of the ammonia is coming into your ground storage tank? You've got to monitor. It doesn't necessarily say you have to monitor there, but you've got to know that if you're going to control the process. So any process that you've got going on in the plant, you've got to monitor. There's just no way around it. You've got to record that data. You have got to keep some kind of record. Some of those records are required, sometimes they're not. But again, if it's a process that you're trying to control, even though the monitoring may not be required, you need it there for your reference so that you know what to do to adjust the treatment process for that particular point in the treatment process. Monitoring plans should be up to date. CT studies should be up to date. Operator logs. You really ought to keep a good operator log. They're invaluable. What's actually happening in the plant? You know, that's very important. Again, it's not necessarily something that's a regulatory issue, but it's certainly something that if I were running a plant, I'd want operators to do for me so that I could tell what's actually happening with my facility. Ladies and gentlemen, I appreciate your time and giving me the opportunity to come and talk with you. They're telling me that that's it. Don's got to stop talking. I almost made it to the end. Thank you again for your attention and hope to see you next year. Thank you.